All right, welcome. Analysis 1A period 8. This is the third block lecture of the year. There was snow yesterday, but fortunately it did not affect our calculus progress. Fortunately it did not. All right, so we're going to do a bunch of stuff. We ended last class, I want to say, what was the last thing we did? Do you remember? Exactly?
It was like the problem.
I think I kind of remember. We did an epsilon delta proof. Basically,
yeah,
and then we did
f of x equals x over 2.
Yeah.
Over x times
Yeah, I remember now. It was like 1 over x, and then you had to, I gave you an epsilon of 1/10, and you would define the delta. Yeah, okay. All right, so here's the thing. We have this excellent, so this is what I want to talk about. This is actually a little bit like left over from the previous lecture, kind of. What? You should title these notes today something like, making the epsilon delta definition work for you. I don't know. No, I don't have a title. Just what we're going to do is, the title is, I don't know, just title it like more limits or something like that. So here's the thing. What I want to talk about is, what I want to talk about right now is all the ways in which a limit can fail to exist. Okay, so ways in which a limit can fail to exist. And we have already seen a bunch of limits which don't exist. But in order to answer the question of whether the limit existed or not, we just used common sense. But what I would now like to do is to use common sense, always, don't ever turn that part of your brain off, but to also use the actual formal definition of a limit. So, for example, let's talk about a classic case in which we usually say that a function has no limit. And that would be jump discontinuities. Jump discontinuities. Okay, so jump discontinuity, you guys probably learned this phrase from Giles last year. It's something like, and we already saw pictures of this, like you have a function, and then at a certain point it just jumps to, at a certain point A, let's say, it jumps to be something else. Okay. So, and let's just say that this y value is L and this y value is M. All right, now, on the very first day of this class, when I was introducing you to what limits even mean, we kind of talked this out, and our conclusion was that the limit as x approaches A of this function does not exist, right? Say right. Right. Yeah. Okay. And our reason, and the kind of thing I expect on your papers, I'm like, well, that's because, the limit as x approaches A from the left of this function is L, but the limit as x approaches A from the right of this function is M. And so there is no one particular y value which I can say that the function is getting closer and closer to. All right, but now, what I would like to do is kind of explore what the advantages are of having this formal epsilon delta definition of a limit. And this formal epsilon delta, well, I don't think we need to repeat it because we did it last class, but what does it say kind of about this one particular problem? So let's, for example, suppose you're talking to somebody who thinks that the limit is L. Suppose we think that, for once, I always set up these like fake dialogues with you where I'm the one who's right and you're forced to argue with me and then I always win. So for once, I will play the role of the wrong person. So let's say that I think that the limit as x approaches A of this function is L. All right, now you have a couple ways of reasoning with me. One way of reasoning with me is to try to just be like, dude, listen, you silly person. The limit is not L because, when I get closer and closer to A from the right, the y values are not getting close to M. Okay, but that's kind of informal, right? And so I might just not believe you because I might just argue back with, no, well, I really think it's L. Okay, and these kinds of pointless conversations can go on forever. And the reason why we will never make any progress unless one of us is just like, taller than the other one or something, or makes threats, or money exchanges hands. There's all kinds of ways that arguments can end in the real world. Someone just gives up. But what the problem with that style of argument is that we don't have a formal definition. Okay, so in this effort that we put in last class to create a formal definition for a limit, we can now actually use to settle these sort of marginal cases. Okay, so supposing I accept the formal 19th century epsilon delta definition of a limit, please explain to me why I am in fact wrong. So I accept the formal definition of a limit, and yet I still think that this limit is L. Prove me wrong. What, Eo, what are you going to do to prove me wrong?
I'm going to ask you to give me a delta such that when the distance from x to delta, when x is between, when x is less than delta away from a, that the limit, that f of x is less than epsilon away from L, and it has to be equal on, and the delta has to be.
Okay. All right, I feel like you understand what's going on, but you're just rambling. I feel like this could actually be settled with a single word. Can anyone disprove me with a single word?
Delta.
No, delta is not the word. That's close though.
1.
1. Is that your word?
Yes.
Yeah. Can you explain? What do you mean? I mean, I actually understand you, so success. But can you explain to the class what is this? What you're just some crazy person sitting in the corner shouting out the word 1. What is she talking about? What is 1?
1 away from 1 away.
Yeah, 1 is epsilon, right? 1 is her epsilon. She's the angry person in the room with the pitchforks and the torches. Did we talk about this? Yeah. And she is challenging me. Okay, now there's no scale on my y-axis, so that you could consider that a problem maybe. But she is basically going to say 1, and I'll just pretend that 1 is about that far away from L. So Emma says, bet you can't do 1, and it turns out that I just can't, right? By demanding 1, what she is demanding via our formal definition is that, because remember, what does the formal definition say? Maybe we should write it. The formal definition says, this is true, if and only if for all epsilon greater than 0, there exists a delta greater than 0 such that for all x, if I am pretty close to A, then my y values are pretty close to L, specifically within epsilon. And thus, in order for me to defend this claim, I have to be able to find a delta for any possible epsilon. But she's challenging me with an epsilon of 1, and already on the first try, I fail, right? There's no way I can do this. There's no way, no matter how close, do you guys sort of feel what's going on here? Yeah. No matter how close to A I get, there's no way that I can force all of these x values when plugged into the function to land between the parallel lines. Because there will be x values arbitrarily close to A on the right, for which, when I plug them into the function, they remain outside the parallel lines. Get it? Okay, so that's how you prove that a particular function does not have a particular limit at a particular place. You just propose an epsilon which breaks it. All right, I think you guys see this. What else? Oh, one other thing. Oh, this is a technicality. So we're kind of going through all different ways that a limit can fail to exist. This is kind of a technicality. So can you quickly graph the function f of x equals root a squared minus x squared? Everybody do that? That's like something you're supposed to know how to do. Sabine, what is it?
It's like, hold on, wait. It's like a little.
I didn't hear what you said, but I think it's wrong. Yeah.
It's a circle.
Yeah, a circle, right?
Yeah, that's like a semicircle, right? Because it's like y equals a squared minus x squared. If you square both sides, then you get y squared. You with me now? So give me a vigorous head nod. Yeah, it's a semicircle. So suppose I give you this limit the limit as x approaches a of root a squared minus x squared. What do we think about this? Yeah, I'm tempted to say 0. It certainly look. Oh, so this is supposed to be a, right? I'm tempted to say 0, but it's kind of like something slightly annoying going on here, which is what? Yeah, what's going on? It's like, Mateo.
So if you're approaching it from like a plus, then you're gonna get a little bit more than a squared, and you subtract a little bit more than a squared from a squared, you get like a negative number.
Yeah, and it just like doesn't exist because we're doing no complex numbers or no non-real numbers in this class, all in analysis 1A and 1B. Yeah, yeah, that's right. It's certainly true that the limit as x approaches a from the left of a squared minus x squared, it's certainly true that that's 0 because just but the limit as x approaches a from the right of a squared minus x squared, what's this limit? Yeah, this does not exist for the sort of technical reason that that function is just not defined for x values that are larger than a. Okay, so we have to kind of make a sort of class rule at this point. I don't think this is not a very important thing. I'm going to spend 10 seconds on this and just move on. But because I just really like this rule which says that the left-hand limit must equal the right-hand limit, and because you need to, the delta interval needs to exist like on both sides of a, then for that reason, and there was a problem or two like this on the limits review 1 worksheet, for that reason we say that this limit does not exist. Everyone cool with that? Yes, yeah.
So what about like arc cosine, where it's supposed to be
Yeah,
infinity
stuff like-
and negative? So that just does not exist?
I don't know. Let's get to that problem when we get to it. What was your example? Let's do like really fast.
Arc cosine?
What about it?
Well, it's going to infinity and negative.
Nope, it's not. First of all, it's
Not?
not true about arc cosine. Okay, good. So more.
I meant that.
Oh, too late.
Yeah.
Moved on.
Wait,
All right.
no.
So
Okay.
what
What was
is
that called? You didn't
what is?
Thanks.
Oh, here's one. Here's another one. What is the limit as x goes to infinity, whatever that means, of sine x? Is anyone bothered that I actually have no idea what the limit as x approaches infinity even means? I'm bothered by that. Are you bothered? Have we defined that in this class?
So we've drawn lots of graphs and lots of stuff has gone to infinity.
No, you're supposed to be bothered. Eo, but you're like slightly bothered? Because what if you're trying to analyze this, right? This actually doesn't this doesn't fit with our definition at all. Because what's supposed to be true is that if I get, really close to infinity, wait, what? Okay, so I think we need to patch that up first. So here's a time where you get to create some math. So here we go. Take the limit as x goes to infinity of f of x and suppose that that is L. I think you have an intuitive understanding of what this means, right? I mean, you should. What is your intuitive understanding of this? Okay, I'll tell you what it is. It's that the y values are getting really close to L, right? So your function looks something like this, let's say. Do you guys agree this picture kind of matches this statement? I think so.
Didn't we define what it meant for sequences?
Yeah, okay, so yeah, that's right. So this is your opportunity to seem really smart because this is actually barely different from our definition of what it meant for a sequence to have a particular limit. So I guess Rabbi Fleischman's going to do it. Rabbi Fleischman, please give me a formal, I'm going to call it epsilon delta style, because it's not actually epsilon delta, but it's in the same sort of style. So this is true, if and only if.
I can suggest some not really delta, but value after which all y values will be within some epsilon of L.
Yeah, let's call it big N.
Yes.
So,
This is true if and only if for some epsilon there exists an x value big N such that
yeah, for any epsilon, right? Actually, maybe we should just do the picture drawing first. If I think that this limit is getting really close to L, then it must be the case that for any epsilon whatsoever that you propose,
that there exists some number big N such that f of x such that x plus big N, x minus big N is greater than 0, and or if x plus big N is greater than 0, then
Wait, can you say it in normal words first? What's special about this number big N?
All the values after it are within epsilon of L.
Yes, all the values after n when plugged into the function lie between, yeah, so I think we can just say that, right? So try it again from the top. For any epsilon greater than 0, so no matter how close to L you're demanding that I be,
There exists some number n such that all values of the function after n are within epsilon of L.
yeah, so there exists some number big N, and as long as I go out beyond big N, so if x is bigger than big N, then
Of x minus L is less than epsilon, or the magnitude of that.
yep, we can do it however you want, right? That no, sorry, that the function lies between L minus epsilon and L plus epsilon. Yeah, cool. You guys accept this as a definition? I accept it. All right. Good. What else? Oh, I remember this other thing I want to do. Too late now. So, by the way, so now I think, now that I have a formal definition, I'm pretty happy now. I have a formal definition of what it means for a function to have a limit so-called at infinity. I'm now willing to answer this question. Yeah, what is the answer to this question? Yeah, what is this function sine doing? Answer, it's just like doing this forever. Ooh, it's a beautiful sine graph. So the answer to this is that it does not exist. Buses, explain.
Because if you choose an epsilon less than L, then you can't have an answer. Because it's just going back from 1 to
Yeah.
1.
Hold on, this sine curve is so bad, I'm like gonna get fired. Try this a little bit better. Okay. So yeah, here's sine, and here's sine, and so let's just kind of do it. So okay, give me what was your informal reason? I wasn't even listening to you.
If you choose an epsilon less than 1, then it never works.
Yeah, okay, but you have to be a little bit careful. Yeah, that's true. But I think the if you start to talk about epsilons, it means you already have some kind of limit in mind, right? So let's just go. I mean, okay, could you imagine being in some conversation with somebody who's like, all right, what is the limit of sine as x goes to infinity? Well, here's what someone might say. They might say, well, you know, sometimes it's 1, and sometimes it's -1, but like it kind of just goes up and down, right? And it spends the same amount of time above the x-axis as just below. Let's just call it 0.
Does it?
I don't know. Yeah, I think so.
I think it spends a little more.
A little more? Whoa. Yeah. So I think that the limit is 0.
Well, you're wrong.
This says I'm wrong. Okay, yeah. So I guess again, I'm kind of repeating myself here, but it is not totally crazy to say that the limit's 0 here, right? In a world in which you do not have formal definitions of what it means for a function to have a limit, and you have these famous in logic math, you'll learn about how these famous geniuses of the 17th century just would say kinds of crap like this all the time, right? They would say, oh, it's more or less 1 because it's like it goes back and forth. Or more or less 0. But according to our new formal definition, suppose I think that this limit is 0. Prove me wrong. Someone different, not Eob or Emma. Give me a one-word sort of
You actually
answer.
need 2 words, I think.
Yeah, you might need like a couple words.
Half.
Ready? Yeah, let's go.
Yeah,
Oh,
let's-
Mateo just ruined it. Oh man, Laura, what were you gonna
I
say?
was gonna say half.
Yeah,
See,
good.
2 words.
That's right. Take a half. If I think that the sign is 0, then Laura challenges me with, and Mateo challenge me with 1/2. And if they challenge me with 1/2, what they are doing is they are demanding that I stay within 1/2 of the number which I think is the limit, 0. But of course I can't do that, right? No matter how far out I go, I will never reach a point where beyond that point the values of my function will lie between -1/2 and 1/2. This function will continue going up and down, breaking through those barriers. So yeah, that's why this limit. So it's not 0, and similarly you can go through that it's not 1. Similarly you can go through that it's not -1. What's very, very hard and technical and complicated and weird is to actually do the general proof that in fact the limit does not exist. But certainly we've showed that it's not 0. I mean, and by similar, if I thought that the limit was 1, what would you say? You could also say 1/2 again, right? If I think the limit's 1, you could again challenge me with a half, and then I would have to make signs stay between 0 and 1, and I can't do that either. Are you guys getting this? Okay, good. So that these are one. This is one way in which a limit does not exist. Another way. This is the coolest one of all. And again, you guys are going to seem really smart because this is a really weird, complicated function. But it's a function that we already talked about. Take the function sine of 1 over x. What does this look like? Yeah, that's when you're all just like furiously like wiggling your fingers. Yes, this function has this kind of shape where as x goes to infinity, you're taking the sine of something smaller and smaller, so it's pretty close to 0. At 0, it's certainly undefined, and then it's going to have roots at like k pi and or 1 over pi and 1 over 2 pi, etc., etc. And I'm just going to assume you're right. Oh, and then it's also odd and stuff. So I guess this kind of looks like it does something where it kind of, if that's 1 and that's negative 1, it kind of like goes up and then jump, and then it does those same things again, and then jump, and jump, and then in between here it just goes crazy. Remember this? Crazy, crazy function. All right, now I think you know what I'm going to ask x. Next, what is the limit as x goes to 0 of sine of 1 over x? Thoughts? Magna, thoughts? No thoughts? Or just no? What's that?
No.
No thoughts? What's your no? Is that a no thoughts?
It's just no.
You just think no. You
No.
just think does not exist.
Yeah.
Okay, prove me wrong. Suppose I think, because after all, this function's going like, right, very, very close to 0. It's just going up and down, up and down, up and down. It's like some infinite oscillation happening. What if I think the limit's 0? Because, I don't know, it's like an odd function. I think I read somewhere in a book that all odd functions that go through the origin.
What? What are you talking about?
I think that's true, right? Is this
Yeah.
function odd?
Yeah.
Yeah, I feel like all odd functions go through the origin.
Yeah, but it's undefined.
It's
Yeah.
undefined, so that means there's like a tiny, tiny hole in there somewhere. But that doesn't affect that doesn't affect the limit. What? I don't know. Maybe there's a hole. I'm not really sure. I'm not sure what's going on. It's hard to even have words to describe what's going on. Yeah, it's probably not a hole. But yeah, it's like craziness. Okay, so let's play the same game. What if suppose I think that the limit as x goes to 0 of sine 1 over x, suppose I think that it's 0. Prove me wrong. I think the whole class should be catching on now.
1/2.
Yeah, again, you can just stump me with an epsilon of 1/2. If you challenge me with an epsilon of 1/2, then what you're saying is, all right, smart guy, if you think that the limit is 0, then what you must do, given my challenge of 1/2, is get close enough to 0, so that's delta, negative delta, such that all of these x values, when plugged into the function, will land between these parallel lines. But I can't do that, right? Because there are x values arbitrarily close to 0, which when plugged into the function are larger than 1/2 and smaller than 0. So this is just false. And a similar argument will show that it's not any other thing that you might think it is. So indeed, this limit does not exist, and I can demonstrate that that's true using the epsilon delta proof. All right. What else? Oh, here's one more. This is one more crazy function. This function is sort of famous. So here it is. Ready? This function is 0 when x is irrational, and 1 when x is rational. Ooh. Whoa. What does this function look like? This is the function which basically asks, am I rational or not? We talked about this in logic math, right?
Well,
I don't think we talked about
what
this
is
one.
like the like me, cause.
All right.
Yeah.
Let's plug in some numbers.
Everything.
Like so here's like 1, 2, 3. Okay, so one is a rational number, so I put a dot at 1, and 2 is also rational, so I put a dot there. 3 is rational, so I put a dot there. But so is like 1.5 rational, and so is like 2.5 rational, and a half is rational. In fact, this is a hell of a lot of rational numbers. There are an infinite number of rational numbers. And in fact, there are so many rationals, they are what's called dense. The rationals are dense in the sense that between every 2 rationals is another rational, right? Because I can take a half of 2.5 and 3, and there'd be another one and another one. So there are so many rationals, it's like crazy. In fact, there's so many of them that they sort of like almost fill up. If you were to look at this from afar, this would just look like, or even very, very close, this would just look like a flat line, right? Because there's so many rationals. And yet,
Okay. There are more rationals.
there are also a lot of irrationals. In fact, it's true that there are a lot of irrationals. And so there's also millions of irrationals, like everywhere here. And actually, between every 2 irrationals are more irrationals. You can prove that. And in fact, advanced math fact, that there are more irrationals than there are rationals. Although that's not actually relevant to this argument, but that is true. So if you look at these 2, they will look as if your function is 2 just straight lines, and they'll be almost filled in, but if you look closely, it's like a sweater. There will be tiny microscopic holes, like everywhere. But there will be, yeah. But when you add all these holes up, you get, well anyway, it gets complicated. Okay, good. Now that we have done this, now I just have a simple innocent question. What is the limit as x approaches 2 of this function?
Wow.
Sneaky question was for
It's slightly sneaky, I guess. Yeah, what's the answer? I feel like it's kind of the same thing again, right? Yeah, the answer is it does not exist. Give me a proof.
right below but also
What do you Oh yeah, suppose I think the limit's 1. If I think the limit's 1, prove me wrong. Again, you can just challenge me with 1/2. If you challenge me, if I think that the limit is 1, so here, I'll write down what I think. I think the limit's 1, then you challenge me with an epsilon of 1/2, then what I must do is get close enough to 2 such that all of these x values land between these parallel lines. Yet, fact, there are an infinite number in any interval whatsoever. There are an infinite number of irrational numbers. So there'll always be some that land here. And if on the other hand, I think that the limit is 0, well then you can also do the same trick, right? So, okay. So this is actually a famous function. First of all, because it's really weird, it stretched the definition of what even a function is. And it was examples like this which convinced people, examples like this and examples like this which kind of convinced people that they needed a formal definition of limit because things were just getting really complicated. Okay. Good. More. Oh, here's something. Let's take this function. The function 1 over x minus 4 squared. What is the limit as x approaches 4 of 1 over x minus 4 squared? Please make a graph of that function, and then answer this question intuitively.
Where can we think about the number? Is that like a rule for all the time? Or is that
Yeah, well here I picked it so that it's working, so it's kind of sidestep that issue. But yeah, I can get into that in a second. Actually, can you erase my board for me? What does this function look like? Have we graphed something like this before? Yeah, what do we call this, Ethan Chen?
What do we call those?
Do you have a name for it? What's it look like? Do it with your fingers? Yeah, it's like volcano, right? It's like volcano. X squared looks like this. So therefore 1 over x squared is going to look like volcano. And then this is volcano moved 4 to the right. So hopefully something like that should be on your paper. And then it's going to be basically like that. Okay, so if that's what you had on your paper, then good. What is the, so what's the answer? Just be bold. Alice Park. Yeah, I think it's infinity. Again, as I say infinity, I also really mean that the limit does not exist, but it's certainly true that this function gets bigger and bigger and bigger. Okay, I would like to be able to say things like that the limit is infinity. So if I would like to be able to say such a thing, then I should probably know what that means. So what I would like you to do now is, again, invent an epsilon delta style definition for what it means for a function to have a limit which is infinity. You know what I'm saying? So here, maybe we can maybe I'll make a separate picture. So here's my separate picture. Here's A, and I would like to say, that the limit as x approaches A of this function is infinity. What really do I mean by that? Give it to me in words. Sandeep, give it to me in words first. Explain the general concept. What do I mean when I say the limit's infinity?
That it goes, actually that.
It can be really informal, man. Just say whatever.
Oh, that it.
Really
It's
informal.
really confusing me. It's
Really?
yeah.
Stephen, really informally, what does it mean if the limit's infinity?
Just that as x values are closer to a, then the y values are just really big.
Yeah. Yep. As x gets close to A, the y values get really big. That's all we mean, right? Sandeep, cool?
Oh, wait, I thought you meant.
No, that's all I meant. That's all I meant. That's all I meant. All right, Steve, say it again.
As the x values get closer to a, then the y values get really big.
How big?
Infinitely big.
Well, I don't know what that means.
As big as you want.
As big as you want. Exactly. As big as you want. Okay, I want them to be m big. Where m is shorthand for massively large number. So Stephen says that as x gets really close to A, that the y values get really big. I say how big? He says as big as you want. I say m. What must you do now if you are defending this claim? If it's really true that the limit is infinity, and I have challenged you with a massively large number m, what must you do to satisfy my challenge?
Take it.
Raymond.
Provide a delta such that if a number is in between a minus delta and a plus delta, the f of x is bigger than m.
Yeah, exactly. If you think that this limit is going to infinity, then and you say that as we get close to A, the numbers get really big. I say how big? You say as big as you want. I say m big. Then what you must do to meet that challenge is get close enough to A such that that is true. Follow? So this is a plus delta, a minus delta, and so if we're going to write this out in words, it's going to be something like this. What must be true now is, where do I start? Class, help me. Shout some stuff out.
For all
There's no epsilon anymore. For all m, in other words, yeah, for any possible massively large number that you might want, really doesn't have to be positive, but whatever.